5, 4, 3, 2, 1.
Hi, I'm Dave Spencer from Mechanical Mashup, and I want to send my phone into space. Okay, well, maybe not really into space, but what's scientifically called near space. And that's still pretty cool, right? Now, so you don't get too disappointed by the time we get to the end here, this video is not going to have the money shot of me sending my phone into space. This is how I have prepared to send my phone into space. The next episode that I put out will have the money shot going into space. At this time, I still haven't actually even done it yet. Now, I've wanted to do something like this for years, but it always seemed cost prohibitive. People have been setting up helium balloons with ham radio transmitters on them, little computers, video cameras, still cameras, altimeters, and all sorts of other stuff, and I just couldn't afford that kind of hobby. But then I got my Android phone and I realized I might be able to do the entire project with just the phone. So I have two goals with this project. Number one, to take a photograph above 100,000 feet above sea level. Number two, accomplish goal number one as simply and as cheaply as possible. Now, in order to accomplish goal number two, I've got to get my phone back. My wife has already threatened to kill me for doing this.
You're all waiting for the clock?
The first thing we need to do is create our capsule. The capsule holds the phone and protects it from both impact and temperature. I use styrofoam. Styrofoam is a great thing to use. It's cheap, readily available, and it's easy to work with. I use my hot wire foam cutter that I showed you how to make in episode number 27. So I just used a straight piece of wire with clips on either end. Gives you a relatively straight cut to cut a big block off of a sheet of styrofoam. And to make it a little better, more perfect, I pinned the blocks together with pieces of wire so they were held in place and then trimmed out. And trimmed them out using a piece of angle iron clamped to the table as a race. Using a square, I made everything nice and straight for my cuts. Push the wire into the block on one side, clamp down my race, slid along the race, and got to where I wanted to be. I pulled the race off and slid the block out. And I had the cavity for my phone. I also cut a smaller pocket on the other side to house the only other passenger on this mission. This mitten heater. At 100,000 feet of altitude, the temperature gets so low that the regular lithium-ion batteries just wouldn't work without some sort of help. Now, to make the porthole for the camera, I bent a piece of wire, poked it through the foam, and then hooked it up to the connectors. Carefully rotated it around. When it cooled off, here's my porthole. You can see here it lines up nicely. Since everything was working well, I created the fasteners for it by just hot gluing Velcro onto the inside. Be careful when you're pushing this down because it gets hot through the Velcro really fast, so I used a hot glue stick to help push. Remember, I had adhesive Velcro on my phone already from episode number 21. I bought some styrofoam cups and I notched them out using the hot wire foam cutter. Then I glued them onto the outside of the capsule. I took a piece of stainless steel 1/16 TIG wire. I know I love this stuff, eh? And I carefully bent it around in the shape and put some loops on it so that I could hang the package from the parachute. I attached a little fishing swivel to that. And this is what you end up with. I realize that this looks like just a couple of glued macaroni pieces away from a B+ in grade 2 art class. But, as you'll see soon, it worked out to be very functional. Now I want to note that I could have attached an external battery pack, which I've already made for my camera. I also could have attached my Canon camera, which I've hacked with CHDK, and I could have taken some videos and some photos with that as well very easily. But remember, I wanted to keep this super simple and just use the phone. Once it's done, take the capsule, the phone, the mitt warmer, and an estimated amount of string and parachute material to your local post office and ask very nicely if they'll weigh it for you. Mine came out to 226 grams, which is almost exactly half a pound. The next step is to figure out how fast we want this to impact the ground. We don't want to break the camera. Remember, step 2, we want the camera back. To do this, I downloaded the free app Gravometer from my phone. I decided to use a benchmark of an 8-foot drop onto a pillow to see what kind of forces were involved with the phone dropping. I was confident that this would not damage my phone. Okay, 8-foot drop, G-force test. Onto a pillow in 3, 2, 1. It came out at 3 Gs. Now looking at the Gravometer's website, they track high scores, and it seems like the phone's accelerometers max out at about 14 Gs. I can only assume that this doesn't damage the phone because people have had multiple high scores at that level. I assembled the capsule with the phone inside it and prepared for a second drop, this time onto a hardwood floor. It's counting?
Yeah.
Okay, a G-force test from an 8-foot drop with the shock absorbers. 3, 2, 1. I was very surprised that the forces came out less than the drop onto the pillow. The Crumple Zone cups do a great job. So now that we're happy with our impact velocity and our G-forces, we need to figure out what that velocity is so we can make a parachute that drops it that fast. So to figure this out, we use the formula instantaneous velocity equals square root of 2 times the force of gravity times the distance fallen. So we dropped 8 feet, which gives us 22.698 feet per second, or 2.4 meters, which gives us 6.8, or just shy of 7 meters per second. Now, why am I doing feet and meters? Well, I'm Canadian, so I've got to have 2 sets of tools in my toolbox. Thanks, USA. Now that we know our descent speed that we want, we can build our parachute. So using this formula here that I found online for determining the size of a parachute, you can see I've got the mass of the package, which I've inputted in here, the velocity that I want it to come down at, 7 meters per second. The rest is all standard numbers, acceleration due to gravity, pi is standard, Rho is an air density at ground level, and the coefficient of drag changes for the shape of your chute. I want to do a dome chute. So it gives us our diameter, converting over to inches here, just about 10 inches will be quite sufficient. So I went on to my 3D software and designed the parachute, 6-panel parachute. I'll have 6 lines on it as well. And with this program I can create the flat pattern. So this is our flat pattern, and it can be scaled up or down depending on the size of the parachute you need to make. So we print out our pattern, and then we cut the outside line, which is actually the seam allowance line. Place it onto your fabric. I chose a ripstop nylon, actually a kite fabric. Once it's traced out, cut it out. You need to make 6 panels. I did 3 out of black and 3 out of blue fabric, just to make it interesting. Once you got your 6 panels, you cut off the seam allowance on your pattern. Place the pattern in the center of each of your panels and retrace. Now you're going to sew along the lines. Put your panels together. Carefully sew each one to the next. At the top I put a little knotted loop of string in, and that will be to connect it to the balloon. I hemmed the bottom, 1 to keep it from fraying, and 2 to give it a little bit of stiffness. Make it stay open. You can see the machine is kind of on the quick side, so if you got to do careful stuff, you do it by hand. Here I'm sewing in the parachute lines, just zigzagging back and forth over the end of the strings. So right now we're on location. We need to test out the parachute. And I have to admit, I was surprised at the size of it. It's a little smaller than I thought it was going to be. So we're going to do a speed check on it, kind of like the Mythbusters do. You can see I've got a camera here that's going to videotape the parachute falling off of this bridge. And when it comes down, it's going to pass by those tape marks. I've got my trusty scientific helpers helping me out with this. And when the parachute passes by the marks on the wall there, we will be able to compare it to the frame rate, just like they do on Mythbusters, and we'll be able to figure out exactly how fast it is falling. Now wait a second, I don't really want to be testing things with my $600 phone. I want to find out the numbers are working before I actually put my phone through the forces. So I went on to Wikipedia and I found out how much an average penny weighs, or even by the year exactly how much each penny weighs. And I counted out 98 pennies, which came out to 226 grams, which was the weight of my package. So wrap that bag of pennies up in a little bit of tape, hang it from the parachute, and I have a great way of testing this without worrying about smashing my phone. Okay, we're going to do drop speed test number 1. In 3, 2, 1, drop! So as our weight falls and passes our tape marks, we'll go frame by frame, and it takes 1, 2, 3 frames to pass 1.5 meters. Now if we plug these numbers into our spreadsheet here, which takes speed equals frame rate times distance divided by number of frames, we find out that we're dropping at 15 meters per second, which is, whoa, a little faster than we wanted to go. In fact, it's about double. Now I really have no idea why the math did not work out here, but oh well. I did some new math and I hypothesized that if I doubled the area of the parachute, I would probably half the speed. I rescaled the pattern and recut out and made another parachute. It only took me about half an hour. 3, 2, 1, drop! Perfect! So if we start here, we go 1, 2, 3, 4, 5 frames. I would guess that's about 1.75 meters. Okay, so inputting this into our spreadsheet, we have a frame rate with this camera of 23.976. The distance we covered there was 1.75 meters, and we did that in 5 frames, so we come up with 8.39 meters per second. I think that is well within our tolerance, and this parachute's a go. That was awesome. I felt like Adam Savage from the Mythbusters. Minus the ginger hair. So now we can get our balloon. I went to habhub.org/predict, and that was a great resource website, one of the best I found. We're going to use burst calculator to figure out what size of balloon we need to get. We know our payload mass is 226 grams, 33,000 meters. That's quite good. That's 108,000 feet, so it's a nice round number to use in this. And I went with 800 gram balloon. Now you can see that gives us an ascent rate of 5.16 meters per second. There's some other good information in here as well. Time to burst, the neck lift, that's important when you're filling, and how much helium we're going to need here. That works out to be about 2 meters in diameter. Now if we go smaller, we get cheaper, but there's sizes that will not be reachable. Just won't work with this, the weight of your payload versus the size of the balloon. It can't get up there. So you can get up into reasonable stuff, but I found like 600 grams would have saved me a few dollars on the balloon, but the ascent rate of only 4 meters per second, I found that a little slow. So from there we go to, I went to at least, scientificsales.com. You can click on their weather balloons, and you can see they have a whole whack. I went down to 800 grams, $69. I bought mine from here. With shipping and everything, it came out to $92. And it came within about 3 days, I think. So this is the setup that we're going to shoot for here. We have our package hanging from 20 feet of string connected to our parachute. The 20 feet of string should reduce the pendulum and swinging around caused by the wind as the balloon rises. So above the parachute, we have 10 feet of string connected to the balloon. The idea of the 10 feet of string is, one, to keep it out of the way so the bursting rubber doesn't tangle up the parachute, but not so far that any leftover balloon remnants hanging from the string could drape over top of the package and obscure the camera. So hardware-wise, we're pretty much set to go, but we still have to come up with a way to tell the phone what to do. Now, I wish I could say I made an app for you guys to download, and I actually tried. I tried to learn how to do it, but I realized pretty quick I was in a little bit over my head. I did realize that there's an existing app called Tasker that is $7, but you know, even if you're not planning on a space flight and you have an Android phone, I highly recommend this app. It allows you to take control and program your phone to do different things. I will create a PDF walkthrough for anyone who does want to try this, but for now, I'll just give you a quick rundown of my launch checklist. Once we've rerun our flight simulation, we've filled the balloon and the capsule is sealed. I will email a text to my phone that starts the camera program. The first thing it will do is take a photograph and email it back to me to show that I have an unobstructed view. Then it will start taking a picture every 2 minutes. Then I'll email a text to start the GPS program. The GPS will turn itself on, get a location, a fixed accuracy, a speed, an altitude. It will log it all into a file, but it will also send that back to me in an email to let me know that the program is started and the GPS is running. At that point, we can let go of the balloon. It will rise at 5.16 meters per second, which means in 13 minutes approximately, it will hit 4 kilometers high. At that point, we will lose all communication with the phone that is out of the range of the cell phone signal. It will continue to rise. Once it hits 8,000 meters or 26,000 feet, according to the internet, that's as high as the military will allow you to get a GPS fix. Other than that, they jam it. And they jam it so bad, apparently, that if you try and get a fix above that, it will lock up your GPS. No problem. I've got a plan for that. So that'll take about 26 minutes to reach that point. Once we get higher, 40 minutes or so into our flight, I will shut the GPS down. I'm actually letting it take readings beyond the 26,000 feet or 8,000 meters because I'm curious to see if it will or it will not get the fix. At that point, I will send a message as well. Even though it's not going to get it, I'm going to send a message to my phone telling it to reboot. We'll get to that more in a second. So 105 minutes into the flight, the balloon should burst and the parachute should open. Now, it is still going to come screaming down with the parachute fully open. There's not a lot of air up there, so it will be falling at over 150 miles an hour. At roughly that time, the GPS is going to automatically turn back on and start taking readings again. I don't expect it to get readings, but it's going to attempt it. We'll see if it does or it doesn't. Now, as it's plummeting to Earth, it will pass 4,000 meters, and at that point, it should get my text message telling it to reboot. It will email me back saying it got the message and it is rebooting. Now, we are only 8 minutes from impact at that point, and it takes about 3 minutes to reboot the phone, so that's going to be a long, agonizing 3 minutes. Hoping everything goes well. As soon as it's rebooted, I will send it a text message to restart the GPS. This time, instead of doing 5-minute increments, it will do it in 2-minute increments. Then I will send an email to restart the camera and it will start taking pictures. The first picture it takes at this point, it will email back to me as well. So I'll get a look to see roughly where it is and maybe even be able to figure out how close we are to the landing zone. After the GPS has run for 15 minutes, it will automatically shut itself down because it should be on the ground at that point, and there's no point in taking multiple readings. We will take a couple readings, but we don't need to take too many. I can also send it a message telling it to give me a fix one at a time at that point. Now, one interesting thing is when I get the fix from the GPS sent to me, it gives the location, but it also gives the fix accuracy, which can be anywhere from 5 meters to 30 meters. So if I plot that onto a map, it says basically you're here within this circle somewhere. So if I take multiple readings over time, it will probably give me different readings for location, but the circles should overlap. Now, if we use this like a Venn diagram, this will allow us to greatly increase our accuracy of where this phone should be and where we should be searching for it on the ground. Hopefully at this point, we find it. Thanks for sticking it out this long. I will post the day I will be launching on Facebook. If you are in the Greater Toronto area and want to join me for the fun, you can. If not, you can follow me on Twitter, and I will post live during the launch and recovery. See you next episode.